Thank you very much.
Awesome. Good evening, everyone. My name is Adil Akmal, and on behalf of my team at the Dunedin Astronomical Society and Beverly Begg Observatory, I welcome all of you, people here in person and people online as well, to the Beatrice Hill Tinsley lecture series sponsored by Royal Astronomical Society of New Zealand. Just a little bit of background. Beatrice Hill Tinsley was probably the best of the best Kiwi astronomer. She did her studies in the University of Canterbury, and most of her, before her time, people believed that our galaxies were fixed and unchanging, and her work proved that our galaxies were actually moving and always changing and even interacting with each other. So her work actually proved that our universe is still evolving. And this lecture series is actually just a commemoration of her contribution to science and astronomy. And I can't think of anyone else better than our today's speaker, Dr. Eloise Stevens, who is a research fellow at the University of Auckland. She did her PhD from England in University of Sheffield on figuring out the shape of stellar explosions. I'm sure she can talk about it way better than I did and way more than I did. Her current work revolves around stellar populations, particularly with the goal to understand gravitational wave counterparts. And now, without further ado, I'm just going to hand it over to our keynote speaker for today, Dr. Eloise. Oh.
I've got my lapel mic. Can you hear me? Yes? Brilliant. I'm going to step off shot just for a second to try and figure out those lights. Manual control, all lights, roar.
Oh, I should have done that, yeah.
Roar. Come on, magic. Let there be light. Thank you very much. All right. Tēnā koutou, tēnei te mihi kia koto, ngā mana whenua o te wāhine ko Pirene tō maunga, no wiwi hao ko Eloise tōku ingoa. Greetings, everyone. My name is Eloise. I'm French from near the Pyrenees originally. So if at any point during this talk my accent gets a little confusing, that's what's going on, all right? We're all okay on this. Now, I'm very grateful that my travels have brought me to Aotearoa, and so I would like to start this talk by acknowledging the people sovereign to this land, and every single one of you here in the room and out on the live stream for sharing your time with me tonight, because I'm going to be talking about one of my favorite topics in the universe, black holes and neutron stars and what happens when they collide. Now, we're going to talk about how they form, what they are, and the strange phenomena that happens when they come together and how we can actually observe them. But before we do that, we need to go back to the fundamentals and ask ourselves, what's a black hole and what's a neutron star, right? Now, you'll have heard maybe that black holes are singularities in the fabric of space-time. That's a beautiful word salad, but it doesn't actually tell you that much, right? But don't worry, if you ever hear a mathematician or a physicist say the word singularity, what they mean is that maths breaks. In that particular region of space or time or whatever, maths that we use to understand the world breaks down. Now, the fabric of space-time is basically gravity with a little bit of spice. Gravity in the Newtonian sense of things is very simple. If two objects have a mass, they attract each other, right? Now, if you're looking at general relativity, things are a little bit different. Anything that has a mass will warp the fabric of space-time, create like a little funnel, if you will. And if an object comes close to that funnel, it will fall in. Now, if you're a planet or a star and you're orbiting around another star, it's very easy to understand what's going on and why they're rotating. It's because they're coming in at an angle with a lot of speed, and so they just spin around the lip of that funnel. The way I like to think about it, it's like these funnels you have at the entrance of museums. You know the ones they have so that you will spend your money back in the days when you still had change in your pocket? If your coin goes fast enough, it will rotate around the edge of the funnel before falling in. But if you mess it up, and the coin does not have enough speed, it will just fall in. Now, it's the same principle in space. If an object is more dense, has more mass in a smaller space, the funnel is just going to be a lot deeper. And you're going to need more speed in order to spin around it. Now, the question is, what happens if the speed you need to be stable around it is faster than the speed of light, which is the maximum speed in the universe? Well, that breaks maths, that breaks physics. And so that's our singularity, that is our black hole. That's why they're black. Even light cannot escape those regions in space. Now, typically their mass is greater than 3 or 5 times the mass of the sun. That's only to do with the way that they're formed. That is not a fundamental law of physics. If you really wanted to, you could take all of the mass of the Earth and turn it into a black hole. You would just have to shove it into a space the size of a marble. So quite the endeavor. Now we're going to have a look at the neutron stars, which are the second densest objects in the universe. And like black holes, they pretty much do what they say on the tin. They are made of neutrons. Now, neutrons are subatomic particles. They are one of the components of the atomic nucleus alongside the proton. Now, the neutrons have a neutral charge, 0. The protons have a positive charge, +1. And if you take the electron that's spinning around the rest, you know, the nucleus to make the rest of the atom, if you combine it with your proton, you're going to get more neutrons. That's what happens in our neutron star. It's a region of space so dense that the protons and the electrons are crushed together. This, by the way, is not a real image. That is very much an artist's impression. So our neutron stars are the second densest objects in the universe, but not dense enough to trap light. They are very, very bright. They can pack 1 to 3 times the mass of the sun into an object the size of a city, about 10 kilometers across. Now, that's very difficult to picture and to imagine. So the way I like to give you a little bit of intuition for it is if one of your red blood cells, just one, was made of neutron star material, it would weigh about as much as Donald Trump. You've got to admit, that's pretty dense as far as things go. So our neutron stars, our black holes, are very extreme objects. But how can you even make something like this? Because space is mostly empty. It's just wisps of gas and dust and a bunch of nothing. So how do you go from that to that? Well, we're going to have to look at stars. Like most things in the universe, they start with stars. They start with a lot of gas that comes together. Now, this is the part of the talk where I ask a little question, and I do a little bit of audience participation. And when, in the before times, before COVID, I would go into the room, wander into the room, and harass you to actually answer my question. Now, for health and safety, I can't do that. So please harass yourselves, raise your hand, and answer my question. What is a star? I'm stubborn, I'm French. We've already established that. So we're not moving on until someone actually raised their hand, right? Gonna do a little dance? Come on! I will start volunteering people. Who said what? Come on! Okay, you go. You shouldn't have picked the first row. What's a star? Huh?
Movie star. Movie star.
Can someone decipher?
Stars are ball of gas and they hang in space to give heat and light.
Oh my God. My French ears have no idea what you just said. I'm so sorry. This is very, very, very awkward. I love it. You try it. Let's see if I understand this New Zealand accent better.
So Neville's reply was that a star is a ball of gas that hangs in space and gives off light.
Yes, that is very true. It's a ball of gas that gives off light in space. Excellent. That's pretty much it. This is the sun. This is our star. And in order to give off a lot of light, it needs a few things. We need some ingredients, and then we need some forces to act on these ingredients. We need a recipe. So the ingredients are hydrogen and helium, which are the most common elements in the universe. That's basically what the universe is made of. There's also a bunch of everything else, just a little bit, a few percent. Now, if you're not familiar with the periodic table of elements for astronomers, It's very simple. You're going to love it. It's hydrogen, helium, metals. The chemists hate us. So the hydrogen, 75% of our star, the helium about 25%, and the metals a couple percent in the case of the sun. It can be lower, it can be a bit higher. But that's just the ingredients. Now we need forces to act on these ingredients. There are two key forces at play. The first one is gravity. Obviously, it's very heavy. And everything is being pushed towards the middle. Now the problem with this is that if it's not stopped, it will just collapse. So we need something to balance gravity. And that's going to be the pressure that comes from the inside of the star that's being given by nuclear fusion. Now, nuclear fusion, very simple. You take 3 light elements like helium. Well, you don't have to take 3, you take a bunch. You take a bunch of light elements, so you squeeze them together, you get something heavier, and you get a whole bunch of energy. Now, that energy does 2 things. It's going to create a lot of heat, a lot of pressure that can balance gravity, and it's going to give you light, photons, that can then make your star shine. So that's our star. That balance between gravity and fusion is essential to the equilibrium that lets our star live for millions or billions of years, or even trillion. And the disruption of that balance is essential to its death. Now, for 90% of its life, the star is going to burn hydrogen in its core into helium. And this is very much the boring part. It's very stable, so nothing happens. The 10% at the end, very interesting. That's when you run out of hydrogen, that's when the balance is disrupted. Now, in order to understand what happens in those last 10%, we need to split our stars into 2 main categories, the low-mass stars and the high-mass stars. The low-mass stars are born with less than 8 times the mass of the sun, and the high-mass stars more than 8 times. Now, this might seem very arbitrary, but actually, the initial mass of your star tells you a lot about how it's going to die. It's very effective. Now, this might be the first time you see stars split into this weird arrangement, but you know stars in both categories. The sun, Theta, obviously, is a low-mass star by definition. And most of the stars that you can see with your eyes in the night sky are actually high-mass stars. So we've got Tautoro here, the 3 stars in the belt of Orion. Now, notice Orion the right way around. Although I'm a northern hemisphere girl, I made sure to put its head upside down. And these stars are high-mass stars. Now, the reason that most of the stars that you can see with your eyes in the night sky are high-mass stars is not that they're the most common. Not at all. They're extremely rare. You only get one of those for every, 200, you only get one of those for 200 solar masses that are created. But they're just so much brighter that they're easy to see from very, very long distances. Now, in order to understand what's going to differ between the low-mass and the high-mass stars, we need to look at a really ugly plot from the mid-20th century. It wouldn't be a physics talk without a plot like this, but I promise I will be gentle, I will explain everything. Now, on the x-axis, this one, you have the mass of your elements. So hydrogen is at the bottom over here, right? On this sense, very light. And uranium is over there, super heavy, lead, plutonium, things like that. Now, on the y-axis, we have what we call the average binding energy per nucleon, which is a bit of a word salad, but it's very simple. Basically, your protons and your neutrons hug each other in the atomic nucleus. And that contains a lot of energy, which you can release in the nuclear reactions. Now, in order to understand how much energy you release, very simple. You take where you came from and where you ended up, and you look at the difference. So if you started with hydrogen, and you made helium over there, you're going up that curve, so you're releasing a lot of energy. Anytime you go up the curve, you release energy. If you split uranium into things that are smaller, you also go up the curve, and you release energy. Now, because hydrogen to helium is a big jump, you can power your star for a long period of time, 90% of its life. But when you run out of hydrogen, and you go to burn helium, the jump from helium to carbon is a lot smaller. And in fact, that jump gets smaller and smaller and smaller. Now, the heavier the element, the harder it is to turn it into something even heavier. You need more gravity, you need more pressure, you need more mass. So the low-mass stars are going to get stuck. They're not going to be able to go past carbon, but the high-mass stars will go all the way up to iron. And that's the problem. Because iron is at the tippy top of the curve, which means that whichever way you go, whether you make something heavier or whether you make something lighter, you're not going to go up, you're going to go down. You're not going to release energy. And so gravity is going to win. The core is going to collapse. In about a quarter of a second, the equivalent of 1.5 times the mass of the sun is going to condense into an object about the size of a city. The pressure is so high that the protons, the electrons are crushed together to make neutrons. That's our proto-neutron star, our baby neutron star. Now, the rest of the star is also going to collapse in a little bit slower, and by the time it reaches the middle, the neutron star is already there, very dense, very solid. And so it's going to bounce off, create a shock wave, and you're going to get a supernova. And after a few hundred years, you can take pictures like these. Now, it would be criminal to do a talk like this without showing my favorite nebulae. We've got Cassiopeia here and the Crab Nebula. Cassiopeia exploded 350 years ago, something like that, 400 years ago. Crab Nebula more like 1,000. And what's beautiful about these pictures is that you can see the neutron stars. See that blue dot here? That's the neutron star. See that absolute chaotic mess of a purple light? That's the pulsar. It's a neutron star on steroids. It's spinning very rapidly and launching a jet, and you can just about see it. That's the X-ray it emits, the same X-rays that allows you to see your bones if you go to the doctor. But obviously, we also need to make black holes. And the massive star, the core of the massive star that turns into a neutron star, might be a little too heavy. It might be more than 2.5 or 3 times the mass of the sun, which is the maximum mass of a neutron star. And if that's the case, it's going to keep collapsing and give you a black hole instead. So essentially, those neutron stars and black holes that we're looking for, they are the corpses of massive stars. They are the corpses of these really rare, really bright objects. But this can't be the end. This can't be the end of it all, because I've only been talking, 20 minutes, 15 minutes, something like that. I've also promised you a merger of black holes and neutron stars. We've only got one so far, one star, one explosion, one neutron star or black hole. We need several for them to merge. Fortunately, the universe is very generous, and most massive stars are born with a sibling. They're born in a pair or triple system most of the time. Even when you're born in a triple or quadruple system, you're going to see pairs, right? There's a sort of hierarchy. They're not just going around willy-nilly, wishy-washy, because otherwise it would be very unstable and it wouldn't last. So we're going to kind of focus on the binary aspect of things because, well, that's what our code does at Auckland, which is convenient. But these binary stars can do very interesting things because they can actually interact, you see. That's another really cool artist impression, which, by the way, is not even of a massive star, but you get the gist, it's the same idea. Those stars can get so close to each other, can get so big, that they can start pouring material onto their friend. And in order to understand that a little bit more, we're going to go back to our picture of spacetime. You know, that tense little grid we had and the funnels we created? Well, if our two stars are close to each other, the funnels they create are going to sort of come together, merge a little bit, create a little saddle point in the middle. Now, in the last 10% of the life of our star, it's going to do very weird things. It's going to expand, it's going to contract, it's going to expand again. And so it can expand so much that it actually starts pouring material onto its friend through that little funnel point. But it can get even worse than that. It can expand so much that it can envelope its friend altogether. See this star? Look at it. That is to scale. The separation of these two stars and their radii are to scale in our models. That's a gift from the actual state-of-the-art models we have at the University of Auckland. The time scale is messed up so that something actually happens, because otherwise you'd be standing there for several million years with nothing happening. But the radii are to scale, and you can see that star expanding absolutely to gigantic proportions, completely engulfing its friend, and the separation of the two stars changing dramatically when it goes through that phase. So we need to understand all of these things in our models to understand the genealogy of these stars. And these interactions are not just the fruit of our theorist imagination, if you will. They are things we can actually observe in the night sky, and a very good example of that is Betelgeuse, because you can actually see the stars going around each other This GIF is taken over a period of 13 days. It takes them 13 days to go around each other. And you can see the stream of gas between the two stars coming in and out of view. So this is real. This is something that we do need to model and that we take into account seriously. Now, our binary stars can both be massive stars. There's no reason why they wouldn't. And so they have the potential of giving us binary neutron stars, binary black holes, et cetera, et cetera. The problem is, if you're going to do that, you're going to go through 2 supernovae. And supernova explosions are no trifling matters. They can release as much energy in one event as the sun will in its entire lifetime. They can outshine their own galaxy. This is a real image of a supernova. You can see the center of the galaxy being about the same brightness. And they can eject the material of the star to speeds of 10,000 kilometers per second. Now, that number is not the highest number I could find in the literature just to impress you. This is an average supernova on a Tuesday afternoon. I have worked with supernovae that go at speeds of 30,000 kilometers per second. So they are beasts. And because they're so powerful, they can actually kick the neutron star or the black hole and do interesting things to the system. They can bring our 2 parent stars closer together. They can kick them further apart. They can kick one out entirely and disrupt the system. That's not good, by the way, because we're trying to make them merge, so not helpful. But we need to take all of that into account. But if you can survive 2 supernovae, then you have 2 neutron stars in orbit around each other in space, ready to merge. But how do you get there? How do you get these 2 objects to actually come together once they've been formed? Well, once again, we're going to go back to the fabric of spacetime. There's continuity in this talk. It's like I thought about it. Wonderful. And we're going to go back to the funnels that come together and form weird shapes. Now, because our 2 neutron stars, black holes, are next to each other, they're going to form a funnel entrance that's more like peanut-shaped, right? If you've got just one star, just one object, the entrance of that funnel is round. In this case, it's more like peanut-shaped. And so as they go round, they stir the fabric of space-time. And there's a very good video for this, which I want to show you. Huzzah! A very good visualization where the black holes are the wheels and the drill powers the orbits of the black hole. And the orange fabric is the fabric of space-time. I'm trying to get the mouse out. Brilliant. We're going to see it in slow motion, by the way. So you can actually see these waves being created and propagated out into that, piece of whatever, plastic. But in space it's the same. It expands out into space. And these waves that are created need energy. They don't come out of nowhere. The energy has to be taken from somewhere. In the case of the visualization, it's powered by the drill. In the case of the binary black holes, it's powered by the orbit of the black holes. Now, that energy is being taken out of the battery of our drill, in this case, unless it's plugged into the wall, and in this case, it's taken from the wall. But in the case of the black holes, the energy is taken away from the orbit of the black hole. So what does that mean? It means that as our neutron stars or black holes rotate around each other, they're going to come closer and closer and closer together until they merge. That's how we get our mergers. Now, these waves are going to ripple out like waves on a pond. That means they're going to reach the Earth at some point, and they're going to wobble the Earth in a way that we can actually detect. Now, it took a few decades for that to work, but it is something that we can now actually observe or listen to. The way you do this is very simple. You take lasers or laser cube. I'm going to be very sad when I go back to Europe and I can't use this joke. It's going to be very disappointing. Now, obviously, there's a lot of maths and physics and engineering and 40 years of scientific advances that go into gravitational wave detectors, but we don't have time for that, and I don't fully understand how it works, so we're going to keep it simple. Lasers and special mirrors. Your mirrors are at a 90-degree angle, the same distance apart exactly, right? That's very important. The other very important thing about your mirror is that they are completely suspended in space but free to move, fully isolated from every motion on Earth, though. They can't be wobbled by a lorry driving past 2 kilometers away, or by the ground shaking, right? You need to take all of that into account, so that the only thing that makes your mirrors move is the Earth wobbling from a gravitational wave. That's what you're trying to detect. So how are we going to detect if one of those mirrors actually comes out of place? Well, that's where our laser comes in. The laser is a very special kind of light that has basically only one wavelength. So if you're not aware, light is both a particle and a wave, depending on what's convenient at the time. In this case, it's a wave, right? So the peaks and the troughs of the wave in the laser are all in the same spot. And that laser is going to get split by a special mirror between these two ends of the detector. So one half goes here, one half goes there, then it bounces back, this one bounces back. They are reunited before they come to the detector. Because they're exactly in the same distance apart, these mirrors, if they've not moved, when the lasers come back, when the beams come back and reunite, the peaks and the troughs are going to be in the exact same spot. And that's all good. But if one of the mirrors has moved, you're going to get a bit of a mess up, bit of a mess, and that's going to create interferences. That's why these things are called interferometers. They actually measure the interferences in the light from the laser. That's how they figure out if the mirrors have moved. But because gravitational waves are very hard to detect, these detectors have to be quite big, you know. In the LIGO detectors, which are the American ones, we've got a bunch of others. We've got one in Italy, one in India now. In the LIGO detectors, the distance of the arm, the length of the arm is 2 kilometers. You can't see the other mirror, it's somewhere over there, it's off the picture because it's so big. And you notice it's in an area not very populated. I think this one's in the middle of a swamp or something. Because you don't want people building and drilling and driving past, obviously. Now, the other wonder of engineering is inside the detector, not just on the outside. You can see the mirror on this amazing pendulum. The mirror's over here. The pendulum's like 120 kilos. This is a really old picture. I wonder if they've not updated it. It's a little far away from me as a science, so I just checked their website. And the reason that you need such complex machinery is because the wobble you're actually trying to detect, the actual motion of the mirror, is 0.0000000000000000001 meter. I think I counted that right, 10 to the minus 21 meters, which is 1,000 times smaller than the atomic nucleus, which itself is 1,000 times smaller than the atom. Which is a bit crazy. I don't know about you. This is the kind of stuff that I look at and I think, back to this quote, I can't remember it verbatim, but it says something like, technology, if sufficiently advanced, is indistinguishable from magic. That's the way I feel about gravitational wave detectors. I don't fully understand how they work. It's a big collaboration that's been working on it for decades. I use their results very happily. And I understand the basic concepts, but the details of it and how they get to that sort of precision, magic. Now, we've been able to see, we in the royal we sense of the word, I haven't, but we've been able to detect gravitational waves for a while now. Back in 2015, in the before times, when the UK was still part of Europe, before Trump became president, and when having Corona was a good thing, we found the first gravitational wave, the first direct observation of a gravitational wave. We had indirect observations showing that they existed, but this was the very first event. And you'll see a lot of these phone numbers in this talk and on the internet. GW stands for gravitational wave, and then this is just the date, 2015, September 14th. Very simple. And this is what it looked like. So there's two panels, because there were two detectors at the time. On the top, we're just going to focus on the left, by the way. They're essentially the same. The top panel is the observed signal, cleaned. And you can see the wave coming in and increasing in strength, and the peaks come closer and closer together. That's the frequency increasing. You can see the frequency increasing here. It's like a chirp. It's a whoop, whoop, just like on the radio or whatever. And the reason the frequency increases in your gravitational waves is because your black holes are spinning faster and faster and faster as they come closer and closer together. Just like the coin, in the funnel. As it's just about to fall in the hole, that's where it spins the fastest. It's the same idea. Now, what's cool as well is that the theory, which is this graph, works very well. Much is really good. This is nice when your theory and your observations come together that nicely. Now, what's great about having theory that works is that your observations can tell you a lot. So what these people can do with just these wibbly-wobbly waves is tell you the actual masses of the black holes. I'm going to have to speed up. So these black holes that came together were 35 solar masses and 30 solar masses, and they made a 62 solar mass absolute beast of a black hole. Now, for those of you that are not asleep yet, you may have noticed that 35 and 30 do not make 62, right? There's 3 solar masses that have gone somewhere. And they've been turned into energy to power the last drags of the gravitational wave, which blew my mind at the time and still blows my mind today. The fact that 3 times the mass of the sun worth of matter was turned into energy in this one event, absolutely tremendous. Now, this event was the first, but definitely not the last. We have seen nearly 100 black hole mergers, nearly 100 black holes since then. This is the stellar graveyard, which is a wonderful plot. There's only one axis. I love that. There's only the mass. You can see 1 solar mass here, 200 solar masses there, and the x-axis doesn't do anything. They just put the shapes in a nice order that makes it look kind of symmetrical and pretty. The blue stuff is the black holes, the black hole masses. Specifically the ones we have detected through gravitational waves. The red ones are the black holes whose masses we know because of typical observations with normal telescopes. Now, as you can see, the gravitational waves have now completely overtaken the typical observations, and they dominate our understanding of black hole masses, which is really exciting. It's a whole new way to see the universe. Now, there's 2 other colors on this graph, the orange stuff and the yellow stuff, and those are the neutron stars. Now, the yellow is the neutron stars we've seen with typical telescopes, quite a few more than the black holes, but that makes sense because you can actually see them, they're bright. And the gravitational wave ones are the orange. And there's only a handful at the moment, and it makes sense because neutron stars, not nearly as massive, so the wobble that they create in the fabric of spacetime, not nearly as big, right? So a lot harder to detect. But we have seen them. And the first one of these was actually the most impressive, and that's the one I'm going to talk to you about now. It was called GW170817 because it happened in 2017, in August the 17th. And it had masses of this. Now, as you might notice, the masses for the neutron stars, not nearly as precise as that of the black holes. We can't really tell them apart. There's just a range for the 2 neutron stars that came together. And the reason they couldn't tell you exactly the individual masses is because it's very difficult with that kind of gravitational wave. But it still gives you a very good idea of what you started with, and it gives you a mass for the final black hole. Now, what's really cool about these binary neutron star mergers is that the neutron stars are bright, they're shiny. So when they come together, they're a little bit more dramatic than binary black holes, which is why they're my favorite. Now, in order to understand what happens to these neutron stars, we need a little simulation. And I've got a nice video here that shows 2 neutron stars coming together. Don't worry too much about the colors, they're probably just density, I'm not sure. But you can see neutron stars coming together in slow motion. And because they're rotating around each other, when they start merging, they're not merging head-on, right? They're going to slowly spiral into each other and then expel a whole bunch of material outwards into space. So a bunch of that material is expelled fully. Some of it creates a donut or a torus around the newly created hypermassive neutron star. That yellow thing is too heavy to stay a neutron star, so it's going to collapse to a black hole when it loses a bit of angular momentum. And that torus, which conveniently we can still see in the vignette, that torus is very cool because it's going to launch jets from the neutron star that's in the middle. So there's a lot of stuff going on. We've got 3 markers essentially. Go on. Yes, we have 3 markers for our binary neutron star merger. We have the gravitational waves, which we've been talking about for a while. We have the jet, which is created by that torus from the neutron star black hole in the middle. And then we have the rest of the stuff that was expelled out from the merger. That's going to create a cloud of very radioactive stuff that's going to shine. And it's going to be called a kilonova because it's similar to a supernova. It's a similar idea. It shines because it's very radioactive. Now, what's very cool about these kilonovae is that they create very important elements for us on Earth. So the periodic table of elements, now we're back into the real world, it's not just hydrogen, helium, metals. We actually have names on this. But we also have colors. And you can see that oxygen, aluminium, things like that are created by exploding massive stars. Those are the supernovae I was telling you about earlier. But there's a lot of yellow stuff over there that's not taken into account. All of that heavy part of the periodic table of elements requires merging neutron stars, or potentially something else. There's people debating it, which is fun, and that's why I still have a job. But we're still trying to figure out exactly where they come from, and merging neutron stars are a very good site for them, because in order to create these elements, you need a lot of neutrons. You essentially need to fire your atomic nuclei by a bunch of neutrons so that they can get as heavy as they are here. And those elements are things that you all know, like gold, platinum, palladium, silver, and rare earth elements that are on your phone that are essential to technology we have today. So it's not just the little drags, the little crumbs of the universe. These are rare elements, but essential elements to life on Earth. Now, in 1708-17, we saw all 3 markers of binary neutron star mergers. We had the gravitational wave. Now, in this particular case, we had 3 detectors online, which was convenient, because we could check the American ones and the Italian one. You can see the American one has the chirp, the whoop, whoop, the Virgo, nothing at all. And that's not because it wasn't online, it's not because it wasn't working, it's because that event happened in the blind spot of Virgo, which was actually a blessing for us, because the blind spot of gravitational wave detectors are actually quite small. And this allowed us to pinpoint the location of 1708-17 like we'd never done before. Because localizing those gravitational waves on the sky, really, really hard. In the past, we had regions like this. You know, this yellow banana, we actually call them bananas. It's actually like these 2 regions of the sky. It's very hard to survey such a large area of the sky. We would never be able to find the jet or the kilonova if we had to actually survey such a big area. But 1708-17, teeny, that's doable. We can do that. We can do that. And they did. They found the gamma ray, so you can see the jump, whoop, merger, and bam, gamma burst. Big deadly laser right there. We also found the kilonova, and that's what I enjoy the most. You can see this is a GIF, August 22nd, August 26th, August 28th. You can see how fast it fades. It's crazy. If you're used to doing observational astronomy and you keep track of how bright stars are, you might want to see what we call the light curve, which keeps track of the brightness over time. This is what it looks like. That's in days. We've got 0 here. And don't worry about the scale, it's just brightness. You can see it peaks very early, less than 2 days, or even less than a day in certain colors, after the event. Which means we're a bit of, we're on the clock, you know. With supernovae, they will peak around here, around there, between 2 and 3 weeks. So we've got time. But with these ones, we're in a rush. But we found it. And that's great, because with this little dot right here, we have, there's a mouse in the middle of my slide. Go away. Very good. Because with that dot, we have the location of the galaxy. And the galaxy is great for people like me. Because if you give me a galaxy, I can tell you the age and the chemical composition of the stars surrounding the event, which tells me about the age and the chemical composition of the parents of the event. Now, this is the part of the talk where I indulge myself and I show you my very own squiggles. This took me 2 years, so take a good look at it. That's what I was hired for in Auckland. And essentially, what this is, focus on the things up here, those squiggles here. That's called a spectrum. It's where you take the light and you split it into the colors of the rainbow. We've got blue here and red over there with the full rainbow in between. And that light comes from around there, around the explosion. Not the explosion itself, around it. Now, you might notice there's no stars in this region that you can see, and that's because they're too far away. You can't see the individual stars, but their light is still around. It's still there, and you can see it. It's just all combined. So it's a whole bunch of stars together giving you that light. But based on the squiggles in that light, I can tell you what those stars are like. I can tell you their age and their chemical composition by finding the right composition of models. And so what this tells me is that we have basically two populations in this particular galaxy. We've got an old bunch of stars, and they dominate 95% of the mass of the galaxy. They're between 3 and 10 billion years old, and their composition is a little bit less metal-rich than the sun. So the sun's about 2% metals, these ones a bit less. 5% of the mass of the galaxy, though, is a younger population, between 800 million years old and 1.3 billion years old. For comparison, the sun is 5 billion years old, right? And these stars are more enriched than the sun in chemical elements. So there's basically been two stages of star formation in that galaxy, two major events that have created new stars in this galaxy. But the old and the metal population absolutely dominates. And it is the one that is the most likely to be the origin of that explosion, not just because it dominates the mass, well, mostly because it dominates the mass, actually, because these ones are, on their own, they're more likely to give that kind of event, but they're completely overwhelmed by the old and the metal poor ones. So with 99% confidence, over 99% confidence, it comes from somewhere in this first star formation event. But that's not it. That's cool information, but frankly, it's pretty boring. If I spent 2 years and I just told you, well, that's what I did for 2 years, yeah, that'd be pretty sad. But what I can do with this information is I can combine it. Oh, I'm doing cardio. I can combine it with the mass of the neutron stars that I was given by the gravitational waves people, and then I can go through all of my models, see what happens to them, which ones actually give me the right parameters, and then rewind the tape and figure out their full genealogy. And so this is what the parents of this mega explosion were likely to be. Now it's all probabilities because it's science, but the most likely system was something like this. Now don't worry too much about the jargon on the slide, like case BCE. It's not meant to be, I took that directly off my new and upcoming publication. So just follow the colors and the sound of my voice, and it will all be fine. So, the parent system, 2 stars, the first one, about 15 times the mass of the sun. The second one, about 12 times the mass of the sun, or something like this. So it was a little bit less massive, but not by much. For 90% of its life, this star does nothing. It's just behaving very nicely, burning hydrogen in its core, and then it runs out of hydrogen and things get weird. And it goes through that common envelope evolution. Remember when it expands massively? Oh no, yes. See where it's going to engulf its friend and change the orbit massively? That's what happens here. And then it's going to keep going through its life afterwards. That has been a big disruption. And in some of the cases, it also goes through mass transfer towards the end of its life, which is interesting, but not all of the time. Regardless, it goes through a beautiful supernova explosion, gives you a neutron star, and then you've got a neutron star and the second one, 12 solar masses-ish. And this one's going to start dying. And it's going to go through the same evolution, very similar. It's going to go through a common envelope phase, and then it might go through mass transfer. Most of the time it actually does, but it doesn't actually make a difference to the system. Now, the reason this is cool is because some of my colleagues are like, oh, it must do this. But I'm like, aha, maybe it doesn't have to. So we'll, fight it off at the next conference. I don't know. We'll figure it out. And then you got your second supernova, you survive that, you've got a binary neutron star system, and 5 billion years later or something, bam, kaboom, gravitational wave, wibbly wobbly, we detect it. And we have a beautiful discovery. Now, this is the only binary neutron star merger for which we have seen all three components of the explosion. So we have a lot more work to do, because this is the first time we've been able to unpack that kind of genealogy for any sort of transient, actually. The codes uncreated are kind of the first time that we've put all of these pieces together. So this is fun, but I've only done it for one. We need to do it for a lot more to understand how these stars form in general, what their parents were like, etc., etc., etc. Which is why I'm asking for money from the UK to keep doing that over the next few years, and maybe I'll come back and tell you all about it in the mid-2020s. Now, it's getting to the end of the talk. I'm tired of listening to myself, and I'm sure you'll too. So we're going to start cooling down. And the cool down is going to be easy. We're going to talk about the last thing that's missing, the black hole neutron stars merging together, right? We've talked about black holes, we've talked about neutron stars, but obviously you can have a black hole and a neutron star next to each other, and why would they not merge? They absolutely would. And we have found those. There's a couple of, the first two signals were in 2020. And in some cases, you could expect these events to be a bit interesting. You know, the neutron star could get disrupted by the black hole, get shredded to pieces before it gets swallowed by the black hole, sorry. And if it does that, then it can do some really interesting things, the jets, the kilonova, kaboom. But in this case, the masses derived by the gravitational waves tell us that the black holes are way too big compared to these neutron stars. And you would not have an event like this. Instead, it would look more like this beautiful visualization from the people at Osgrav in Australia. And that's actually a very nice visualization of gravitational waves, and we'll end on that. So you can see the gravitational waves, they're distorting the light in the background. And as the black hole and the neutron star come closer and closer together, they're spinning faster and faster, the gravitational wave frequency increases, and then all of a sudden, the neutron star gets swallowed by the black hole, and the gravitational waves slowly die out. Now, this is based on simulations. This is not just a pretty picture. They've actually done the maths. Do you want to see it again? Yeah? Do we want to see it again? Oh, why? Half the time it plays it again and half the time. That's why I have a mouse. Oh, what? Do your job. Go away. Yes. It's fun to try and figure out, you know, when is it going to come together? You've seen it once already, but you never know. And that breakdown is true, by the way. The fact that it keeps wobbling for a little bit after it's been swallowed, that's actual physics. You can see it in the gravitational waves. All right, so we're going to end on that and do the questions very soon. Before we do, I would like to take just a minute to thank some of my amazing colleagues at the University of Auckland, particularly my boss, Jan Eldridge. She's amazing, but everyone else is as well, and some of them are missing because they didn't send me their pictures. It's their fault. If you could give me feedback sometime at the end after the talk, that would be great, because I can put it on my CV. Thank you very much. And if you've got questions that I can't answer this evening, then just hit me up on the internet. That's what I do. And on this, I'll thank you very much for paying attention to this talk. All right, questions. Don't be shy. Yes.
Very fun merger where the neutron star disappears inside the black hole. What sort of time scale is that?
God, the echo makes it extremely difficult to understand what you're saying. Can you say it again without the microphone? Sorry.
For the very
end.
Part of the merger,
Yeah.
the neutron star disappears inside the black hole. What's the time scale along?
Or what's the time scale for the neutron stars disappearing inside the black hole? So I think that's in real time. I want to say that's in real time, actually, this one, but I'll have to double check. But it's similar scales to what you see in We're talking milliseconds. We're talking seconds in the case of neutron star mergers and milliseconds in the case of black hole mergers. So quite small scales, but not as small as the space scale. Like in terms of time, it's measurable. Yeah. What happens to the neutrons when they're absorbed by a black hole? That's a very good question. The neutrons that are absorbed by the black hole just go into it, and then what happens? We don't know, because we can't see inside the black hole. Now, particle physicists will all have their own grain of salt to add to this. The neutrons are not sustainable in a black hole environment. They kind of dissolve. Exactly what happens to that matter, it's very difficult to say exactly. Is it just a soup of quarks? Is it something else? Because inside the black hole, the math breaks down. It tends towards putting everything down to a point, but obviously it doesn't really make sense physically for everything to go down to a point. It's still matter, but exactly what happens, like maybe a particle physicist would have some really kooky, nice, fun ideas to give you. As for me, it's more of a, think of the neutrons as kind of dissolving into their particles, and neutrons are a bunch of quarks together, and so the concept of a neutron kind of disappears. And maybe those smaller particles survive, but maybe they don't. Questions, more questions? Questions from the online?
Yep, we've got one. It says, when two neutron stars merge, do they behave the same as just a normal neutron star?
Do they what, sorry?
Do they behave as just an ordinary neutron star?
Oh, in what sense? So they get squished a little bit, so they're not around anymore when they start merging. But I don't know if it's a question about the effects of gravity, because gravitational mass and baryonic mass are not the same. There's a lot of things that...
it doesn't say so.
It's weird. So one of the essential things is they get distorted very significantly. Because the shape of the funnel essentially gets distorted. It turns into that peanut shape, right? So the stars follow it. And it's very unusual for neutron stars to be deformed in any way, shape, or form, because they're extremely dense. But in those very extreme regimes, they do get that kind of tear-shaped sort of thing towards the end. More questions? Yeah.
I think it should.
Why that one stage is optional. So why is it optional for you, and why would they say it's essential?
That's a very good question. One to which I don't have a full answer to, which is why we'll have to duel it out. But let me talk a bit more about that. So what's the main difference between my colleague stuff and my stuff? So this is a very specific genealogy for that specific event. In the past, people had thought about mapping out the genealogy of binary neutron star events, but in more kind of generic sense, just kind of generic models, not trying to fit anything specific, maybe trying to fit generic populations of binary neutron stars. Anyways, it was more like big picture stuff, and not modeled from beginning to end, which our models do. We model the whole thing from beginning to end. Obviously, we have assumptions in some places, and they're a little bit different from other people's assumptions. The main uncertainty is this, the common envelope. When it swallows its friend, it's very, very uncertain what's going on in this phase. It's a very active area of research at the moment, and I think that once people figure out some of these details, it's going to revolutionize stellar evolution models to an extent. The main differences between my stuff and my colleague stuff is the channels that they'd put together in the past only had one common envelope evolution phase. So this seems kind of repetitive, et cetera, but it's actually really interesting that they go through very similar phases and that they can still successfully give you the binary neutron star. Because in the past, people had said, well, you get a common envelope here, but here you don't, but you get this instead. And in my models, you get common envelope everywhere in over 90% of the time. And you get this some of the time. And even in that, some of the time stuff, it doesn't necessarily make a big difference. Like the stellar winds, which I didn't talk about because we don't have time, also play a very important role. And all of that is to make sure the mass of the star is, like the parent is the right mass to give you the final neutron star. Stellar winds is essentially the star just shedding its outer layers, like a, I don't know, what's a dog that sheds its hairs a lot? Newfoundland? I don't know. But yeah, it just sheds its outer layers on its own because it's just too bright. It pushes the material outwards with a lot of force. And that does the job just as well as this mass transfer. So there's a lot of uncertainties, the main one being this phase. And once we figured out a consensus on what's going on in this phase, then we might start finding similar-ish channels. But at the moment, it's different, which is good. For me. Like, science, it's great when we come to a consensus at some point, but if you go into a new field and everyone agrees immediately, it's like, well, okay, well, I guess we're done now. So it's nice that there's some exciting stuff we don't understand. That's why I have a job, you know. Thank you very much for a good question. Any other questions? Back of the room, yes. I can't see the back of the room. I'm blinded.
Are these mergers only likely when they were born as binary systems, or would they see roaming black holes from separate systems collide before they evaporate?
Oh my god, I need subtitles. Can you shout it without the mic? I'm sorry.
Yep. Are these mergers only likely when they were born as binary systems, or would we see roaming black holes from separate systems collide before they evaporate?
Very good question. So, the stuff I do is with the binary systems. That's what we do at Auckland, stellar evolution from binary systems. So that's the only thing I talked about. But yes, the idea that maybe black holes come together without being born together is also an idea. It's called dynamical interactions. Dynamics just means things are moving, right? So basically they're moving inside a cluster and all of a sudden they meet each other like, ah, boom. Now, you would never get a head-on collision. That's not something that can really happen realistically in space. It would be like the probabilities of that are infinitesimal. But it's more likely that you could have, for example, at the stage where you have the supernova, you kick that neutron star out. And it could end up wandering inside the cluster, so stars are born in groups, not just with siblings, but in like big households, big families, millions of solar masses often. And the heavy stars tend to fall towards the middle of the cluster. It's like falling at the bottom of the hill in terms of gravity. And so the neutron stars might, and black holes especially, might end up, if the density is very high, might end up being close enough to each other to like catch another black hole and make a really weird system after the fact. Now, these systems would have slightly different properties. First of all, it's most likely that those black holes coming together would have a very high, what we call eccentricity, which is actually, well, I can use one of my slides. It's not made for it, but it will give you an idea of it. It's when the orbit is not round. So where we have this. See how this is an ellipsoid and not a circle? That's a very elliptical orbit. Basically, things are moving in ellipses instead. And it's because, you know, they would have just caught each other kind of, like, you know, in passing. So they end up with these weird ellipsoids at first. The other very important thing, because their ellipsoid will die down eventually, by the time they merge together, it's basically round. But the other very important characteristic is that black holes might spin at very different angles. So yes, black holes can spin, neutron star spins as well. And it is something that is somewhat measurable by the gravitational waves, the alignment of the spins. Now, if your stars are born together, because they're from the same cloud of gas that spins the same way, and then the cloud of gas splits into two and you get two stars, but because they have the same kind of angular momentum when they're born, they spin in the same way, their spins are aligned. If your two black holes were not born together, they will have random spins. There is no reason why these should be aligned, so they could be completely different. And so that is something that people are trying to measure with gravitational waves, because that's what can tell us what proportion of these events are from binary interactions like I showed you, or dynamical interactions. From my perspective at the moment, it seems that most cases will be born together. It's kind of difficult to catch something that's flying past. In a cluster, you would need a very dense environment. It would be very difficult, but it is not impossible. And finding exactly what fraction of systems come from one root or the other is going to be one of the things that the field is looking at in the next decade. It's a very good question, Internet. Anything else?
I'm just sort of curious what kind of your background and what kind of got you to where you are now, sort of into studies, skills.
So what's my background and how did I get here? Very good question. I do wonder that myself sometimes. No, I'm kidding. So I'm originally from France. Like I said, I did all of my schooling in France until I was 18. And then I moved to the UK to do my undergraduate. I moved to the University of Sheffield in the north of England. I did my undergrad there. I did an integrated master's, which means that technically I don't have a bachelor's. I didn't graduate from my bachelor's. I just went straight to the MPhils. I did 4 years in a row. That 4th year, I was lucky enough to be selected for a student program in the Canary Islands. So through the University of Sheffield, I went to the Canary Islands for a whole year to work on a big telescope called the Isaac Newton Telescope and be a support astronomer there, which means that astronomers come in and they're like, I want to use the telescope to observe this. And I'm like, okay, let me show you how. And I just stayed with them for the first night, making sure that everything was all right. Did that for a year, and then I went back to Sheffield. They got me back for my PhD, which I completed in 2019. And then I came to Auckland to work with Jan Eldridge at the university. And that's kind of how I got here in terms of skills. Math, physics, coding, Python, learn to code if you want to be an astronomer. For some of the more senior generations, Fortran. I code in Fortran. A lot of these codes are in Fortran, and a lot of it is actually from the late 60s, early 70s, so it's still in Fortran 77. So we have loads of legacy, very interesting codes as well. So a lot of cross-disciplinary things are happening in that field of astronomy to get these results. One more question from the online.
We've got one more question
Yes.
online. Have the scientists recorded any mergers close to our solar system? And the other question is, will there be any consequences for life if they are recorded near a solar system that harbors life?
I still have no idea what you said. Just show me the thing.
It's going to be hard to read.
Thank you very much. Yeah.
Second one.
Second one. If the scientists recorded images close to our solar system, will there be any consequences for life? Blah, blah, blah. Okay. So am I the only one who did not understand the question, or do people want me to repeat? Me to repeat? Yeah. So have scientists recorded any mergers close to our solar system? Will there be any consequences for life if they are recorded near a solar system that has life? And it depends how close you mean and what orientation that system is in. The gamma ray burst can be quite powerful, but obviously, in order for us to detect it, we have to be down the jet. If we're here, we can't see anything. So we were, for that particular event, we weren't like around there, we were more like here. There was a bit of an angle thing. But it was 40 megaparsecs away times 3. I forget, those 120, is that right? 120, 150 million light years away? Something like that. So, pretty safe social distancing happening there. Now, how close exactly you'd have to be in order for life to be in danger? I don't have an answer on top of my head, but my immediate intuition is, given how empty space is, it's not something you'd need to worry about. And given how rare these events are, that so a supernova, you've got 2 supernova per century in something like the Milky Way, and these events are like 1,000 times rarer. So you'd have to be pretty unlucky to be in the same part of the galaxy, which are really big, and for it to happen right next to you. For that part, is it dangerous to life? Yes, if you're really, 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 really unlucky. Have we detected something near the solar system? It depends on what you mean by near. Because 40 megaparsecs, which is this galaxy, so 120 something million light years away, that is very nearby for me. Look at how big the galaxy looks. You can take an actual picture of it because it's so close. It's very, very neat. But obviously, different astronomers have very different definitions of nearby. I have friends who work on galaxies that are at the very edge, the very early universe. So for them, this is basically next door. My partner works on white dwarfs, little tiny stars in the galaxy. And for him, anything that's like 200, 300 light years away, you're starting to get a bit far because you can't see them at those distances. So it very much depends on what astronomer you're talking to. I would say that this is pretty near the solar system, or pretty near the galaxy rather, because we can get such a beautiful detailed picture of the galaxy and get nice information from it. Now, with the next generation of gravitational wave detectors, we're going to be able to see things that are 2 to 3 times as far away, some of the time. So we are getting a really nice upgrade, and the new observing run of gravitational wave detectors starts this year, at the end of the year, if everything goes well, otherwise it will be early 2023, and it will last 1 year. And what's going to be great is that hopefully we're going to get more of these. We're going to get more of these binary neutron star mergers that have the 3, events, 3 components that we can detect. And if we do that, or if at least we get a nice picture of a galaxy, then I can do more of my work and get a lot more advances in this field. Anything else from the room or anywhere? I'm going to put my mask back on so I don't give you COVID.
All right. I think it's as good a time as any to wrap it up. Before we finish, just a few things. First of all, Dunedin Astronomical Society and Beverly Begg Observatory is a 100% community run and a non-profit. We have a donation box at the door there, so we always appreciate all the help we can get. And now it's time to thank some of the people who made this possible. So first of all is the Royal Astronomical Society of New Zealand, who do a lot of work to make this possible every year, these lectures. Second is our hosts, Otago Museum, who are always kind and are very friendly with us, who give us the space to run these lectures. And the third one is people from Dunedin Astronomical Society. So we've got Anton and CJ there. We've got Peter and Ash. They really did a lot of work to make this all possible. And obviously, finally, our guest here, Dr. Eloise. So I think we should all thank her.